My area right now of research in my PhD program is developing a method to detect and measure functional information encoded in DNA and proteins, and then analyze that information to see what application it has within biological life. For example, in proteins, to see what relevance that information has for the three-dimensional structure of proteins and their function. And it's within the context of that research that some of the things that I'm sharing today will emerge. Just by way of overview, I want to begin with defining some basic concepts and going through some definitions. Then I want to move into the next section of my presentation, which will be the role of intelligent design in science, and then move from that into the concept of functional information, and then apply that to biology in an effort to develop a method to detect intelligent design. So let's begin with the first major section, concepts and definitions. And can't see it very well on the screen there, but there's a molecular machine called kinesin. Can you see that? Can you see a molecular machine working there on the screen? Is that bright enough? I think I'll just skip that and just move on to the part you can see. I want to define intelligent design as an effect that requires a mind to produce. An effect that requires a mind, an intelligent mind, to produce. And for example, the operating system Windows Vista. Now, those of you who use Macs may have some questions about how well designed Windows Vista is. Some of you may think it's suboptimal. You will say, well, if it was really a product of intelligent design, it wouldn't do this or that or the other thing. However, I don't think anyone would dispute that it is actually a product of intelligent design. There was a team of computer engineers, software engineers somewhere working for Microsoft that produced that. So Microsoft Vista is a product of intelligent design, even if it's not designed the way you would prefer it to be designed. Another example would be the Sphinx. Here again, we have a product of intelligent design, but when we look at the Sphinx, we notice that there has been significant deterioration in that design. So much so that it has undergone at least 2 major restorations throughout history. So if the restorations had not occurred, the deterioration would be even more pronounced. Nevertheless, in spite of the fact that that design is susceptible to deterioration and has undergone significant deterioration, again, I don't think too many people would dispute that the Sphinx is a product of intelligent design. The alternative that we have for explaining effects is mindless natural processes. And I'm not using mindless in a pejorative way or denigratory way. I'm simply using that word to contrast that with products of intelligent design which require a mind. The other option are processes, natural processes, that do not require a mind. And to emphasize that is why I use the term mindless natural processes. Those are the 2 options that we have to explain effects. I suppose there's a third option, that would be nothing caused the effect. I would reject that option as an irrational option, and furthermore, it's a science stopper. That is, if you say nothing caused that effect, then you automatically rule out science from having anything to say about any explanation as to how that effect came to be. But primarily it's irrational, so I reject the concept of effects occurring that have no cause whatsoever. So these are the 2 major options that we have. I want to define design detection as the scientific discipline of detecting whether or not an effect requires intelligent design or not. To expand, it is the scientific discipline of detecting whether or not the effect requires a mind to produce. And if it requires a mind to produce, then by definition, it is a product of intelligent design. Examples we've looked at thus far, Windows Vista and the Sphinx. I want to present also the intelligence hypothesis. The intelligence hypothesis states this: an attribute that distinguishes intelligence from mindless natural processes is the ability of intelligence to produce significant or produce effects requiring significant amounts of functional information. I think that's probably self-evident. if we thought about that, that would probably be the determining factor that marks the determining attribute or characteristic of intelligence, the ability to produce not just low-level functional information, but very significant levels of functional information. That hypothesis then leads to a method to detect intelligent design or design detection. You need two things. Given that intelligent hypothesis, you need two things. First of all, you need a method to measure functional information. And secondly, you need a method to estimate what a significant level of functional information would be. So the intelligent hypothesis is the attribute that distinguishes intelligence from the mindless natural processes is the ability to produce effects requiring a significant amount of functional information. When you think about that, the next two questions are, how do you measure functional information, and what do you mean by a significant amount of it? And we will look at that shortly. Another essential thing to understand is the distinction between science and philosophy, and I'm finding today that the majority of scientists who are opposed to intelligent design have utterly failed to make this distinction. The job of science is to come up with a scientific method to test for intelligent design. That is the job of science. That method then needs to be applied to the object or the sequence under investigation. For example, in the case of the Sphinx or Windows Vista, we could subjectively say that looks to me like a product of intelligent design, but the job of science, if it's to be rigorous, must develop a generally accepted method to test for intelligent design and apply it to the object or sequence under investigation. That method will either indicate that this effect has a high probability of intelligent design, or it does not have a high probability of intelligent design. It may have a low probability, but it's not high enough to warrant jumping into the higher category there. That's the job of science. Then, if it does have a high probability of intelligent design, the next step that science needs to take is to apply another area of intelligent design, which I refer to as design derivation or reverse engineering. And that occurs when you start with a complex system that's already operative, and you slowly dismantle and analyze that system to reduce it to basic operating principles. If it does not have a high probability of intelligent design, then of course it follows that it must be or is capable of being produced by mindless natural processes, in which case you can start from first principles of physics and explain that effect, such as a bolt of lightning or the crystal structure of sodium chloride. That's the job of science. In either case, there may be philosophical implications. That is where philosophy and theology begin. But what I find is when I'm discussing intelligent design with many scientists, they will say and claim on scientific grounds that intelligent design was not required for the origin of life, or was not involved in the origin and diversification of life. My first immediate question to them is, if you're going to make that claim on scientific grounds, what was your scientific method to test for intelligent design? I find that most scientists have not even thought that they needed a method. What they have merely presented was an assertion, that is, a conclusion without any scientific argument that supports their conclusion. Now, the same goes for me. If I'm going to claim that biological life requires intelligent design, the question can also be leveled at myself. What scientific method did I apply to biology to justify my claim or my prediction that life does require intelligent design? But in the meantime, I want us all to be crystal clear on the distinction between science and philosophy and the roles that both have in this question. We'll come back to that diagram from time to time. Now I want to look at the next major section of my presentation. That is the role of intelligent design in science. And the reason that I want to look at this is because I have often heard scientists assert that intelligent design has no place in science. So is that true? There are three major areas where I believe intelligent design does have a role in science, and the first one is in design application. That is, using intelligence in science, applying that to a scientific problem, either the experimental constraints that you need in a lab to have a successful experiment, or producing something. And the example that I have here is the artificial genome that's just been created by the Ventnor Institute, where they have used intelligence to create an artificial genome, M. genitalium. That's one application of intelligent design in science. That's where you have an intelligent agent creating a genome, and we already have one example of that with the Ventnor Institute just having announced their accomplishment of that. The second major area where intelligent design is involved in science is design derivation or reverse engineering. In 1976, the free world did not have access to the new MiG-25, the state-of-the-art Russian fighter, until Sergei Belenko defected and flew his MiG-25 into Japan and landed at an airfield there. The next step was to very carefully dismantle that MiG-25 to figure out how it was built, how it worked. Perhaps the largest reverse engineering project, it is their largest reverse engineering project that we have ever embarked on, is genetics. We start with a finished product, and systematically we analyze the cell, we analyze DNA, we analyze proteins to try and understand how the cell works, how biological life works. The third area where intelligent design is involved in science is design detection. That is the area I want to focus on for the purpose of this seminar. The first two I will not. I merely mention those, but when the question is raised, is biological life a product of intelligent design, that involves this third area of design detection. So is design detection part of science? Design detection centers around the question, remember what intelligent design is defined as being, that is an effect. An example of intelligent design is an effect that requires a mind to produce. So design detection centers around the question, could mindless natural processes produce this phenomenon, or does it require a mind? And the underlying assumption there is, we already know, and it's an empirical fact, that intelligence can produce a virtually or apparently unlimited amount of functional information. We do it all the time. Whenever you write an essay, for example, you produce a very significant amount of functional information. And when you fill up your hard drive, it's filled up usually with a significant amount of functional information. We know that the probability that intelligence can produce high degrees of functional information is 1. We've observed it so many times, and we actually are capable of doing it, of reproducing it, that we know intelligence can do it. The real question is, can mindless natural processes do that? And that's what we apply in these areas of science. Number one is the SETI Institute in their search for extraterrestrial life. As they monitor radio or optical signals from deep space, the question that they're dealing with, is this signal a product of intelligent design or not? Or is this signal produced by mindless natural processes, or is there intelligence out there somewhere? The central to SETI research is the question of design detection. That is absolutely essential. The next area that I would suggest it's used in is forensic science. A man is found laying on the floor with a knife in his back. The forensic scientist must determine, is this effect a product of mindless natural processes, or is foul play involved? And foul play is, in this case, equivalent to intelligent agent was involved in producing this dead man on the floor with a knife in his back. So if one is to argue that intelligent design has no place in science, it suddenly demolishes the whole science of forensic science. A forensic scientist would then be forced to come up with only mindless natural explanations for examples of a man laying on the floor with a knife on his back. And SETI Institute would have to close its doors because the presupposition is there is any signal that you would ever receive from deep space could only be explained by appealing to natural processes. Next area is archaeology. Here's an example of some church samples. To the uninitiated, these church samples appear to be just pieces of rock. However, it's actually been determined by archaeologists that these are ancient tools, and they have their reasons for arguing. Essentially what they're doing is they're arguing that these are not, in fact, products of mindless natural processes. They are products of intelligent agents who lived a long time ago, shaped the edges of them, and their argument is based on the edging of some of these church samples. And therefore, they're not a product of mindless natural process, they're a product of intelligent design. or intelligent agents, in this case human. The problem of design detection is also relevant to biology. It has been raised for a number of years now. The question, is biological life a product of intelligent design? And many people, I was in a conversation with a very well-known, internationally well-known hardcore Darwinist, and I mentioned to him the need to develop a scientific method to test for intelligent design that could be applied to biology, and if that was done, the issue would be resolved. And he told me that he would oppose any effort to develop a scientific method of intelligent design detection and apply that to biology. But that is no longer possible. That cannot be opposed any longer with the introduction of an artificial genome. What Ventnor did to distinguish their artificial genome from naturally occurring ones was they incorporated 5 watermarks into that genome, that is, nucleotides that when translated into proteins and using the standard protein letter symbols would spell those following 5 words or 5 names, 5 nouns. And the assumption behind it is that this would distinguish this genome as not a product of mindless natural processes. They've put these watermarks in there. So now, whether we like it or not, we are now faced with the probably growing challenge of determining which genomes, which proteins are artificial, which ones are not, which ones can be produced by natural processes and which ones are not. And that entails or gives rise to the necessity of developing a scientific method that we will be able to use, even in cases like this, to argue or to determine whether or not a given genome or a given protein is the product of intelligent design or it's just a simply product of mindless natural processes. So what I've argued up to this point is intelligent design detection is already an essential part of areas of science. One other example, several years ago, I worked for the National Defense Research, and my job was to write software that would monitor recordings, acoustic recordings taken underwater in the ocean. And the whole point of the software was to distinguish between natural noises, and the ultimate objective was to detect Soviet subs. This was back in the time of the Soviet Union. So I was writing software that would monitor underwater signals, filter out all those that were just due to mindless natural processes, and output those that we felt would be from an intelligent source. And in our case, we were particularly concerned about Soviet subs. So for many years, intelligent design detection has been involved in science. It's essential to certain aspects of science. Now, recall my intelligence hypothesis that a distinguishing attribute of intelligence is the ability to produce effects requiring a significant amount of functional information. So that gives rise to the question, how do we detect functional information? How do we measure it? Just within the past year, a paper was published in the Proceedings of the National Academy of Science that for the first time laid out a definition of functional information and a mathematical equation that we can now apply to any problem in science, whether it's in forensics, whether it's in archaeology. In this case, their application was in biology. Several years before that, a fellow by the name of Jack Szostak wrote a short article in Nature saying, it is now time that we developed a method to measure functional information in biology. Because in biology, traditional methods of measuring information do not detect or not distinguish between functional and non-functional information, but in biology, functional information is very important. And Szostak is the final author in this paper that was just published in this past year. And there it is. For those of you that are not mathematically inclined, you can just admire the form, maybe hang it up on your wall sometime as an art form. But just to explain briefly, EX is the degree of function required to produce the effect. MEX is the number of different configurations that achieve that effect. And N is the total number of possible combinations, both functional and non-functional. Now let me give you an example to help clarify what they mean by this. Imagine that grandfather dies and he does not leave you with the combination to his safe, and you are his heir. So now you've got to break into that safe, and essentially what you need to know according to illustrate this concept of functional information, the first thing we need to know is how many numbers are involved in the combination. In this case, we'll suggest there are 3 numbers, each number of which can range from 0 to 99. That then tells us what n is, the total number of possible combinations. If there's 100 options for each number and there's 3 numbers, it's 1 million possible combinations, and so you've got your work cut out for you. The next thing you need to know is how many of those combinations will actually work. And let's suppose, recall that there's a level of efficiency, and if the combination exceeds that level of efficiency, then it's functional. Let's suppose you got a sloppy mechanism, so that instead of just 1 combination working, if you're within 1 number of the proper number for each of the 3, it actually works out to 27 combinations will work. That then, we just simply plug it into Hazen's formula that he published in PNAS, and it turns out that you will need 15 bits of functional information. That's what you will need to open the combination on grandfather's safe. Now, the next thing that we need to do is we need to know, that answers the question, how do we measure functional information? And that, remember, there were 2 questions that arose out of the intelligence hypothesis. Number 1 is, if the attribute of intelligence is that it can produce significant amounts of functional information. Number 1, what is functional information? That has been defined by Hazen and his colleagues. We've just looked at that. The next question is, what do you mean by a significant amount? And the reason that question arises is because in a blind search, through random chance, you could accidentally generate a certain amount of information, low levels of information. Let's say you had some generator of combinations, random number generator that would randomly generate combinations for grandfather's safe. And if you had enough time, you could actually open that safe. Chances are you could open that safe. If it could generate 1 or 2 million combinations, you have a very good chance of opening grandfather's safe. But you would need enough time to be able to do that. And so what we can do is there's certain criteria that we look to generate to figure out what is a significant amount of information. Because an intelligent agent, we know, seems to be able to generate an unlimited amount. Natural processes or random processes or a blind search is very limited, and it's essentially limited by the number of trials that are available to it to perform the search. In this case, the search for the proper combination or one of the 27 combinations that will open the safe. So M there represents the number of trials natural processes have in a given physical system. Once we have estimated that number, we can then plug that into this equation here and estimate what a reasonable amount of functional information nature is capable of producing. And once we know that figure, then if the effect requires less than that amount of information, then we could say, well, the effect does not require a significant amount of information to occur. Random chance could do that, or a blind search could do that. So that's one of the essential things we need to be aware of, is some way to compute or estimate what a significant amount of functional information is. With that in mind, here is the scientific method I'm proposing to detect intelligent design that would be applicable to any application within science, whether it's archaeology, SETI, forensic science, Ventnor's genome, and so forth. If the functional information required for the effect is greater than or equal to the amount of information that nature could accidentally produce, then intelligent design is not likely to be required. And the reason that I'm stating that is because if it's not greater than what nature is capable of producing, then it's possible that mindless natural processes could have produced the effect. So if it is, I misread the symbol. That is, if the amount of functional information is less than, then intelligent design is not required. If the amount of functional information is greater than what we could reasonably expect nature to produce, then intelligent design might be required. And how far beyond ISIG the functional information is, the natural processes become increasingly unlikely to be able to produce that effect. So it's not a hard cutoff level. Rather it's a transitional zone, and the further you go past that zone, the more information that's required to produce the effect that's greater than ISIG, then the less probable it becomes that nature could produce that. And I'm granting that the probability that nature could produce levels of information up to and equal to I-seg, I'm granting that it's 1. Now in real life it isn't 1, it's much less than 1 as you approach I-seg. But just to not stack the deck in my favor, I'll say it's 1. Now let me talk briefly about probabilities. In their paper that's just published this past year on measuring functional information, what they state is that probability is at the core of measuring functional information. It is at the core of the equation. In other words, that ME over N represents a probability. That's at the core. So there's no way we can escape dealing with probabilities in measuring functional information, at least according to this paper published in a peer-reviewed journal. The greater the difference is, the more likely intelligent design becomes, although you can never say with absolute certainty that intelligent design was required due to the nature of probability itself. For example, the probability may be 1 chance in 10 raised to the 80,000th power, but you could still get lucky on the very first try and produce the effect. So you can never say with absolute certainty that intelligent design is required. All you can do is say it's highly probable. In fact, it's this many orders of magnitude more probable that intelligent design was required than mindless natural processes could produce the effect. So now let's apply this to biological life. The first thing we need to know, remember, we need to calculate I-seg. And in order to do that, in other words, I-seg represents what a significant amount of functional information is, or which is equivalent to what is the amount of functional information nature could reasonably be expected to produce. And recall that in order to do that, we have to know how many trials are available to nature in a blind search. Now I want to get to natural selection next, so don't be too concerned here that I'm forgetting about natural selection. We'll get to that right after this. But first of all, we have to know how much information can be produced in a blind search. Given very generous estimates published in various papers, we can derive that an upper limit for the number of trials available to the origin of life here on Earth, if we make very generous assumptions regarding time, 4 billion years, population size, 10 to the 30th, which is thought to be the number of organisms that live right now on the Earth, and most of that are bacteria. The non-bacterial forms of the prokaryotes actually form only a minority compared to the bacteria. The replication rate, in fact, it wouldn't even 1 order of magnitude. It wouldn't even raise the thing 1 order of magnitude. Bottom line is the total number of trials for an evolutionary search that's been available is 10 to the 42 trials. In other words, if you're going to appeal to natural processes to generate life and produce the full diversity that we witness today, including all those life forms that have gone extinct, you must be able to do it in 10 to the 42 trials or less. That's what we have. That's the boundary conditions for the problem. Now, one other thing we need to look at here is the concept of natural selection. Over the years, natural selection is attributed with numerous attributes that are seem to be intelligent and design-like in their capabilities. In fact, there have been other papers published in science journals saying, look, we need to stop using these terms when we're talking about Darwinian evolution because they're using design terms, such as selection and design. They're often used in evolutionary scenarios. Now, one of the problems that we have faced in the past is that natural selection is only vaguely understood by most evolutionary biologists up until maybe a decade or two ago. One of the things that has really helped add rigor to this area is the computer science area of evolutionary algorithms or genetic algorithms. And that has forced us to sit down and think about things like fitness and fitness functions and how natural selection would work or any other kind of selection would work. And because the reason it forces us to think about these things is that in evolutionary genetic algorithms, you actually have to write computer code that will solve a problem. And the moment you have to start writing computer code, you can't start just writing creative stories anymore. That computers don't run creative stories. They need to have some sort of tracks to run on that will help find the answer. And one of the things we've learned about selection processes or guided searches as opposed to blind searches is that both biological evolution and evolutionary algorithms require what's known as a fitness function to work. Without a fitness function, the search then degenerates into a blind search. The thing that distinguishes a search from a blind search and converts that into a guided search is this thing called a fitness function, and here's a definition taken from an evolutionary algorithm textbook. It's stated as, and I'm quoting here, it represents the requirements to adapt to. It forms the basis for selection and thereby it facilitates improvements. More accurately, it defines what improvements means. From the problem of the task-solving perspective, it represents the task to solve in the evolutionary context. Now, with that in mind, since the fitness function, whether it's found in nature or in genetic algorithms, must contain the requirements to adapt to, or that define the desired outcome, it must contain at least as much information as much functional information as the desired outcome. If it falls short, that shortfall must be made up for with a blind search. And that's the problem we face with any kind of selective search, any kind of guided search, is that the fitness function must encode at least as much functional information as your desired outcome. If it falls short of that, then the shortfall must be made up for in a blind search. If the shortfall is too great, your evolutionary algorithm will not work if you have insufficient numbers of trials. And the more it falls short of that information, the more it becomes a blind search until eventually it degenerates into just a blind search. Now, the amount of functional information, see, if I was to ask an evolutionary biologist about natural selection, the first question I would ask is, where is the fitness function? Which is really an unfair question to ask, because nobody who concerns themselves with biological evolution actually knows where this fitness function is. We can describe effects of this, but we do not know where it is. It could be there. I'm granting for the sake of the argument that it may be out there somewhere. The next question is, how do we measure the amount of information encoded in this fitness function? Again, we don't have that kind of information to know. That might be out there, it might not be out there. But there is a solution to the problem. Since the fitness function must contain at least as much information or more as the desired outcome, the way we can measure the amount of functional information encoded in the fitness function of nature, if it's out there, is to measure the functional information in its output. So, for example, if a particular protein is required by biological life, and there seem to be a certain number of proteins we call universal proteins, they are found in all life forms, and for that reason there is an assumption made that they would have been part of the last universal common ancestor. The thing you need to know is that a little over 70% of all proteins are globular, or they have a stable three-dimensional structure. And that enables them to be functional within biological life. But what you really need to know is that the structure of proteins is determined by physics, not biology. In other words, any evolutionary search that biology performs is essentially looking for the combination to grandfather safe. And combination to grandfather safe in this analogy, that if you apply it to biology, is set by physics, not biology. That's very important to know. So the proteins that we have today, we can't just look at them and say, well, the reason we have these proteins as opposed to some other proteins is that that's just what the search found. No, what the search must find, the protein combinations are predetermined by physics. And any evolutionary search must find that. And if certain proteins are required for biological life, let's say one protein is, the fitness function of nature, that is natural selection, must have encoded within it the information to find that particular protein. At least sufficient amount of information that the shortfall, which must be made up in a blind search, is capable of finding it. If two proteins are required for biological life, then the fitness function must become increasingly complex. Additional functional information must also be encoded in the fitness function so that it can find not just one global maximum or global minimum, to use evolutionary algorithmic terms. It must also find two, must find both of them. In real life, a minimal genome is thought to require at least 382 proteins. So the fitness function of nature must have encoded within it a significant amount of functional information that will help define or help search, so that the functional information that will be required to find those 382 proteins. Bottom line is this: the fitness function of nature is not exempt from intelligent design detection. So the question is, if you believe natural selection, and most people, most people will be unanimous that a blind search will never produce biological life. There's pretty much unanimity there. We're constantly appealing to natural selection. So if natural selection did it, then the question now shifts to, is intelligent design required for natural selection, the fitness function of natural selection, to produce biological life? And the answer to that question is, number one, measure the functional information encoded in its output, and what that will tell you is the amount of functional information that must be encoded within nature to produce intelligent life. If it does not contain that amount of information, nature is going to have to produce go through it in a blind search. So now let's estimate INAT for biology. Recall that we had 10 to the 42 trials. That's the upper limit for the amount of trials nature has had available for it here. When we use that equation published by Hazen and Zostak, what we find is that nature in theory is capable of producing effects up to 140 bits of functional information. And I want to remind you that 10 to 42 trials was unrealistically generous. There is some work being done both computationally and in the lab to find out what the real number is. It's probably closer to 40 bits. That is the upper limit for the total amount of information for any one particular effect and any one particular evolutionary search that nature is capable of generating over 4 billion years in the amount of time and number of trials and so forth. 40 bits. But to be generous here, I'm sticking with 140. So that's I-sig. So now what we need to do is we need to apply this to any problem where intelligent design detection is required to see if the output is greater than I-sig. In the first case, I want to look at 4 cases. Case number 1 is Ventnor's watermarks. From occasion number 1, we plug that in there. We plug the 5 watermarks in there, and that's relatively easy to do. And it turns out that the amount of functional information encoded within the Ventnor Institute's 5 watermarks in their artificial genome is 259 fits of information, or functional bits. Since INAT is 140 bits, or functional bits, obviously the amount of information required to produce the 5 watermarks in Ventnor's artificial genome is significantly larger than the amount of information nature could reasonably be expected to produce, and it follows that it's 10 to the 36 times more probable that Ventnor's watermarks were produced by intelligent design rather than natural processes. So this doesn't prove, let's say a court case began, some lawsuits, copyright infringements over these artificial genomes, and the question was, can we prove that these are actually Ventnor's watermarks and they weren't just accidentally generated in some replication, mutational, deletional, insertion event? And we could use this equation, and when we apply the equation, it doesn't prove that Ventnor inserted these watermarks, but it shows it's highly probable by 36 orders of magnitude. And so the most rational position to take in this case is that Ventnor's watermarks are a product of intelligent design. Let's look at case number 2. Doug Axe has published an estimate for the frequency of occurrence of stable protein domains, stable structural domains for proteins in sequence space. And the best case scenario is that when you look at all of sequence space, the set of all possible sequences that could code for a protein domain, there is a subset that will give you a stable structure that's functional. And that subset, in its best case, is 10 to the minus 64th of all of sequence space. Well, that automatically gives us MEX over N. That gives us the number of functional sequences versus the total number of sequences available. We input it. It turns out that we would need perhaps between 213 and 256 fits of information. Using INAT of 140 bits, we see that the functional information required to produce a structural domain for a protein is greater than what nature is reasonably expected to produce, and it's greater by 10 to the 22 times. That is, it's 10 to the 22 times more probable that intelligent design was required to encode the sequence for stable structural domains in the genomes of life than it was a product of a blind search. Now, if one is to invoke natural selection as the mechanism that produced these, then we have already seen rigor demands that there is a fitness function encoded with nature that must include that amount of information, 213 to 256 bits. So what we do is we then apply this method to the fitness function of nature, and just for one protein domain, we see that the fitness function will require vastly more information than what mindless natural processes is capable of producing, and that will have to be made up by intelligence. We know that intelligence can do this. It's an empirical fact. Probability is 1. The question is, can natural processes produce this? And we've already worked through what ISIG is. Case number 3, the average protein. These are two universal proteins that are roughly average in length. It turns out that SEC-Y requires 688 fits of information, REC-A 832 functional bits of information, vastly more than what nature's natural processes are capable of producing. Using the same method, it turns out that it is about 10 to the 165 to 10 to 208 times more probable that intelligent design is required for these two universal proteins than natural processes. So what I'm arguing here is that the most rational position to take is intelligent design is required, because we already know, in fact, that it works out to about an average of 700 functional bits of information for the average protein. Now, this is not an argument, we don't know what can produce 700 bits, therefore God must have done it. No, we already know intelligence can do that. Every time you write an essay, just one page of text significantly exceeds 700 bits of information. So you yourself can do that. And what is it about you? It's the fact that you're sufficiently intelligent to generate that kind of information. The real question is, can natural processes generate this? And there is no rational justification to believe that natural processes can. Even if you appeal to a fitness function, to natural selection, you will require a fitness function, and that fitness function will require at least 700 bits of information just for one protein. But we need more than one protein for life. As I suggested earlier, you need at least 382 protein coding genes at an average of 700 fits per protein. You need a little over 250,000 functional bits of information for the simplest life form. And so when you see the difference between what natural processes can reasonably be expected to produce and what intelligence can produce, it is about 10 to the 80,000 times more probable that intelligent design is required for the first life form than it is natural processes would produce it. Case number 5, the evolution from fish to amphibian. There has been a suggestion here. In fact, it's not a suggestion. There was a lot of excitement generated by the discovery of this particular fossil, and I was watching an interview with a scientist who was responsible for it. And as a person involved in bioinformatics, see, evolution must occur at the level of changes in functional information in the genome. So the first question you would ask is, if you want to go from a fish to an amphibian, what you must know to present your case is what the information changes will be. How much functional information do you need to go from a genome of a fish to the genome of an amphibian? And what rigorous science needs to do here, and I know my supervisor would have never allowed me to publish these papers that are being published, suggesting this, because he would say, Kirk, before you can publish a paper, you must look at the genome of a fish, the genome of an amphibian, some representative one, determine what the changes in functional information are, and then see if these are plausible. This is plausible. It might be perfectly plausible. Maybe that did occur that way, but if it is going to occur, there must be some sort of natural selection that goes on, which will require a fitness function. We need to know how much information that fitness function has to have encoded within it to produce the necessary changes, produce the novel proteins, for example. So the bottom line is how many fits are required. We don't know this in this particular example, but what we would do is that's the first step of rigorous science. We've moved way beyond just looking at morphology, structural requirements. We know where evolution must occur. It must occur on the level of information encoded in the genomes. Now, you might have noticed that Probability is at the core of functional information, and there's no escape from that. And some people have suggested that probability is not really a problem. Recently, it is in fact a problem. Many people insist it's not, but it is a real problem, and it emerges from time to time on a regular basis in the peer-reviewed literature in science journals. The most recent one is put forward by Koonin, where he concedes that there are no compelling scenarios that exist for the origin of replication and translation. He's looking at the origin of life here. So he promotes a new possibility here, and that is that there are perhaps an almost infinite number of possible worlds out there, infinite number of worlds, universes out there. If that is the case, then I nat, using my term here, I nat becomes significantly greater than what I calculated for. I just calculated for the planet Earth here. I've got an appendix here that does it for the entire universe. It's of no help in finding even one average protein. So you're going to need an almost infinite number of universes to do this. And Eugene Koonin, molecular biologist, suggests in this journal here that that's the only way out of this problem. What's interesting is to look at the comments of the reviewers, which are also published online. One of the interesting things about them is the a priori commitment to not allow intelligent design into the solution of the problem. That's interesting. It's an a priori thing. It's a philosophical commitment, nothing to do with science. In fact, I would argue it's very bad science to rule out intelligent design a priori. It would be bad science in the case of forensics, in the case of Ventnor's things, in the case of SETI and so forth. It's bad science in this case. But what's really interesting is they say any scientific hypothesis must be testable and refutable. It is impossible to test for other universes. And therefore, when one postulates alternate universes, they've left the realm of science and are now entering the realm of philosophy. A good scientific hypothesis is minimal. You go with the simplest explanation. This is the opposite. Koonin's suggestion is the opposite of the simplest explanation. He invokes an almost infinite number of unseen, untestable entities. And also, finally, the reviewers suggest that it should be probable, and this is where every origin of life theory fails and why Koonin produces his alternative hypothesis. It must be probable. Well, if we're going to take a minimal approach to this, the simplest explanation is we already know intelligence can produce vast amounts of information. I myself have built proteins, although I did use a natural template for it. I've built proteins from scratch. Granted, I did use a natural template because they are incredibly complex. We're not at the position we can build a completely novel protein from scratch, but we may well be there someday. We just need to increase our background information about how folding occurs. So we already know intelligence can do this. We already have a simple explanation on the table. We know it can produce evolutionary algorithms. Conclusion, it is extremely probable that intelligent design was required for biological life, and the probability is so highly in favor of intelligent design that I would argue the most rational position to take at this time is that an ID was required. Now, what I see the problem here in this whole controversy is a philosophical assumption that many scientists make, and that is for mindless natural processes, what we see is that effects can be described by simple equations. The crystal structure of a lattice, sodium chloride, for example. A bolt of lightning actually reduces to simple equations of physics, and we can totally understand that starting from first principles. Biological life, on the other hand, cannot be described by simple equations. Yet science has assumed that the explanation for the origin and diversification of life was its territory so far as intelligent design is a priori ruled out. And that is an arbitrary decision, and it's a double standard within science when in other areas of science, say in forensics and archaeology, in SETI research, for example, intelligent design is not a priori ruled out. In fact, it's central to those sciences. But when it came to biological life, there was an a priori decision made: we will not allow intelligent design into the discussion, design detection. But what I've already shown is the production of an artificial genome by the Ventnor Institute has now, like it or not, made it necessary to bring intelligent design detection into biological life. And the moment we start applying that, it not only successfully identifies Ventnor's watermarks as a product of intelligent design, but it also identifies the proteins, the average proteins of life. And I've only looked at proteins. And when Darwin first postulated his theory, we knew virtually nothing about the cell. And this, what I've presented today, is not a result of a problem of what we do not know. It's what we do know that is creating the problem. And every month in journals around the world, more discoveries are being made regarding molecular machines and even molecular computers that will, with chemical inputs, compute the cell fate, future fate of a cell, activate certain genes, deactivate others, and direct that cell in that direction. We are seeing a higher and higher degree of functional information, which has led two scientists by the name of Abel and Travers to publish another paper in the Proceedings of the National Inquiry of Science saying, look, chance and necessity will not produce the first life form. And PNAS actually published this a few years ago. And their whole reason is that what we're seeing now in the genome is cybernetic encoding. It is, in fact, it is the most impressive piece of software, more impressive than anything humans have ever written. What we once thought was junk DNA, more and more of that each month is found to have some regulatory function within the cell. True, there may be a significant amount of deterioration over time that may be occurring, and it may not be designed the way you and I would have designed it, but it's simply because that's often the case when you're looking at extremely complex software that you don't properly understand. So the bottom line is, it's not a question of, well, we don't know, therefore let's appeal to intelligence. Bottom line is this: we know intelligence can encode, can write computer code, and to the extent that when you apply the information equations to it, published by Hazen and colleagues, we know we're capable of vast amounts of intelligence, and we assume that it's not just us. When we do a SETI research, we assume that any intelligent agent is capable of producing significant amounts of functional information. And when we apply that to the increasing number of discoveries we're making in biological life, it's increasingly obvious that natural processes are pathetically short of ever being able to write computer code and encode that kind of information. That was the gist of Abel and Travers' argument in their paper that I published about almost 3.5 years ago. I want to conclude with this overhead here. Get back, when I look at this discussion, I'm constantly hearing this is religion, not science. Now, I want you to recall that up to this point, I've said nothing about God and religion. We have just taken cold hard physics, cold hard information theory, cold hard bioinformatics, empirical observations, and we've applied that the same way we might apply it in forensics or in SETI, and we've applied that to biological life, and it seems to be coming up ID positive. But when I'm talking to scientists who object this, or I'm reading articles in the newspaper, their objection, this is religion, not science. And recall that I argue that they're conflating two fields, philosophy and science. We must be careful not to do that. If intelligence was required for biological life, so be it. We need to deal with that. And the philosophers and the theologians can wrestle with the theological and philosophical implications. In either case, there will be philosophical implications. But that's the job of the philosophers. The job of science is to come up with a method for intelligent design detection that's applicable across the board for all areas of science, apply it to biological life, and decide whether or not it's coming up ID positive or not. But what I've presented here is not proof that intelligent design was required, because recall, probability is at the core. We could have gotten fantastic